And we are back. All right, today we're going to talk about the fourth quantum number first, which is the electron spin quantum number, which is referred to as m sub s. Okay, so if you remember from last class, the first quantum number n, the principal quantum number was what energy shell you were in, and remember that was a positive integer. The next one, the angular quantum number L, was the subshell you were in, which was those possible values from 0 to n minus 1. And then finally, the quantum number that determines the orientation, m sub L. Remember, those possible values are from negative L to L. Okay, then finally, the electron spin quantum number, m sub s, that determines in an orbital there are two electrons, and they have to have opposite spins. Okay, one we say is spinning up, and one we say is spinning down. So spin down, and so we assign the one that's spin up a value of positive 1/2, the one that's spinning down a value of negative 1/2. Okay, and this principle is called the Pauli exclusion principle, meaning that no two electrons can have the same set of 4 quantum numbers. So I'm going to show you later in the week how we assign those 4 quantum numbers when we're filling in the electrons in a particular atom. Okay, so this means an orbital can hold 2 electrons, and they must have opposite spins. One will be spin up, which we assign a quantum number value for m sub s as positive 1/2, and the other one is spin down, which we assign a value for as negative 1/2. And we talked about the end of last class. Within each energy level, within each shell, we have these different subshells, and we said they were equal energy, or we would say another term for that is degenerate, meaning all the different subshells within a given shell are the same energy. However, this is not true. This is only true for hydrogen, so it's not true for any other atom. So that means in each energy level, in each shell, these different subshells actually have different energies. Okay, and for each one of these, when we're filling in the electrons here, we'll have a different quantum number. Okay, and one way with the m sub s quantum number, if it's pointed up, that means it's going to spin in a clockwise direction, and if it's spinning down, that means it spins in a counterclockwise direction. And we'll go over how we determine that later on this week. Okay, so the reason why in these different shells, these different subshells have different energies is for 3 different reasons. So we know in a sodium atom, meaning it's neutral, it has 11 protons and 11 electrons. So let's say if we think about if there's an electron right here. So there's a couple different energy contributions that are affecting that one electron. So we know the negatively charged electron, it's attracted to the positively charged nucleus. So the first energy contribution we have to think about is that attraction between the electron and the nucleus. So that's one thing we have to think about. Second thing we have to think about, we have 1 electron here, but that means there's 10 other electrons all around outside this nucleus in this electron cloud. So that means since they're like charges, since they're both negatively charged, it's repelled, that 1 electron is repelled by the 10 other electrons. So what we call that shielding, because this electron is not bound, is not as close to the nucleus as it otherwise would be if no other electrons are present, because all these electrons in here, they get in between this electron and the nucleus, and they push that electron farther out than you otherwise might predict it might be. So both of these energy contributions are potential energy. The third one, we know these electrons are moving, they might not be moving around in orbits, but they're still moving around the nucleus. So we also have to think about the kinetic energy of the electron as it moves around the nucleus. Okay, so we have to make sure we balance those three energy contributions. There has to be a balance between the nuclear attraction and the repulsions of the other electrons. Okay, so sodium is an example of a polyelectronic atom, simply meaning an atom that has many electrons. So any atom besides hydrogen. So atoms with more than one electron. Okay, and remember, we now know the electron pathways are unknown. It's not like the Bohr's model. Those electrons are not traveling around in orbits. Okay, so we can't calculate that exactly. But now we can place them in their different subshells, the orbitals S, P, D, and F. And I will tell you the energy for each energy level. The energy of the S is less than the P, which is less than the D sublevel, which is less than the energy of the F sublevel. Okay, so that is true for any shell. Okay, so the reason for this, if you look at the following graph. So this is the radial probability distribution. Remember, we talked about that last class in terms of the different shells around the atom. And just looking at this, you might think, oh, okay, 2p has a shorter distance from the nucleus than 2s at that maximum height. So, okay, that means 2p will be the lower energy subshell. But if you look at this little hump here in the 2s sublevel, this is called the penetration effect. So what that means, it causes an electron in the 2s sublevel to be more attracted to the nucleus. So what that means 2s is lower than energy than the 2p. So 2s is lower in energy than the 2p sublevel because of this little hump. Okay, and for s orbitals, these number of humps indicate what energy level you're in. So since it's 2s, that means we have two humps in this graph of radial probability. Okay, so when looking at this graph, even though 2p, its maximum is closer to the nucleus, its most likely spot is closer to the nucleus, with the 2s, we still have to take this into account as well. Okay, so we say the 2s penetrates to the nucleus more than the one in the 2p orbital because of that hump. So as a result, it's more attracted to the nucleus. Okay, so even though the maximum of the 2p is closer, the 2s, even though it spends a small amount of time in this little hump, that's significant enough that it lowers the 2s energy lower than the 2p. Now, if we look at the 3s, so third energy level, so now there's 3 humps in here. 2 small humps, 1 big hump. And think about 3s, that average distance is going to be farther than it is for the 2s. But comparing this 3s curve to the 3p and 3d curve, so now 3p has one little hump here, one source of the penetration effect. So for p orbitals, the number of humps is the energy level minus 1. Okay, and for the d orbital, notice there's only one maximum here. The number of humps is the energy level minus 2. So that means for the third energy level, that's why there's only one hump for the 3D. So looking at this, the 3D, the 3P, and the 3S, you might think, okay, the 3D is lowest in energy. But because of these little two humps here for the 3S, that's lower in energy. That's the lowest in energy, and then the one little hump of the 3P, that makes it lower than in energy than the 3D. Okay, so in terms of the energy, 3s is less than 3p, which is less than 3d, due to this penetration effect. So in general, the more effectively an orbital allows its electrons to penetrate, the more humps you have down here, the more it allows that electron to get closer to the nucleus, to that nuclear charge, the lower the energy of that orbital, because the farther and farther out you get, it causes a higher and higher energy. So now looking at these different energies of the different sublevels, in each energy level, these different subshells now have different energies. So as we see here, the 2s is a lower energy than the 2p. And then for the third energy level, it goes s, then p, then d. So they all have slightly different energies. And next week, I'll show you how to fill in this energy level diagram with electrons. All right, that's all for this time. See you next time.